Well, welcome back to the 23rd Annual New Jersey Department of Transportation Research Showcase. I'm Ted Green with Rutgers Kate, and I will be your moderator for this, the virtual poster session. This session is being recorded and can be watched later by visiting NJDOT's Technology Transfer website. We have 8 poster presentations on various topics for you this afternoon. The poster presenters will have an opportunity of responding to your questions at the conclusion of the presentations. Please place any questions in the Q&A pod. I do ask that you indicate the poster topic when you ask a question so we know which presenter needs to address it. Our first poster presentation is titled Hot-in-Place Recycling of Asphalt Pavement, Current Practices and New Technology, and is presented by Rutgers University's Chen.
Hello everyone, my name is Chen, and my presentation topic is about the current practice and new technology in hot-in-place recycling of asphalt pavement. Hot-in-place recycling, which is also called HIR, has been widely used in asphalt pavement engineering because of its low financial cost and less consumption of new materials. Heating is an indispensable process in the HIR, and currently infrared heating is the most common heating method because it can heat the pavement to a high temperature and in a short time. But when we use HIR, the pavement must be heated to the softening temperature before mixing, placing, and compaction. Although the infrared heating can heat the pavement quickly, it transfers the heat through heat conduction, so it often causes the defect of surface cooking and internal unsoftening. So recently, microwave heating has been proposed as an alternative to infrared heating because the microwave heating has advantages of rapid heating rate, short processing time, and no air emissions. And more importantly, the microwave heating can avoid overheating the pavement surface and can heat deeper material of the pavement. So in order to evaluate the potential applications of microwave heating in HIR, this study investigated its heating characteristics and compared them with the infrared heating by laboratory experiments and numerical modeling. In order to determine the material properties, the laboratory experiments were conducted first. The thermal properties are actually needed in infrared heating modeling, and the electromagnetic properties are needed in microwave heating modeling. So based on this, the thermal property test was conducted to measure the thermal conductivity and the specific heat capacity of the material with different gradations. We can see in figure 3 and 4. Totally, there are 4 different asphalt mixtures that were typically used as surface course in New Jersey, and they were investigated in this study. Different geometry specimens of them were made for the test. The microwave heating test was conducted to measure the temperature after different heating times, as shown in figure 5 and 4. Figure 5 and 6. The heating results were further used to back calculate the electromagnetic parameters of the material in the numerical model. So after obtaining the material properties, the numerical modeling was conducted to compare the heating characteristics between microwave and infrared heating, including their temperature distribution, heating rate, and energy consumption. As shown in figure 7, when the power increased from 5 kilowatts to 15 kilowatts, the time required to reach the same temperature for microwave and infrared heating decreased by around 67% and 92% respectively. So it shows that the effect of power on the infrared heating is more remarkable than the microwave heating. But the microwave can heat the asphalt pavement to a greater depth, while the infrared heating can only heat the pavement to a maximum depth of about 3 centimeters under the power of 5 kilowatts. And also, the temperature gradient along the vertical direction in microwave heating is much smaller than the infrared heating. And from the heating rate point of view, in general, different asphalt mixtures did not have remarkable difference in the heating rates in both microwave and infrared heating methods. But the microwave heating rate was comparable under different temperatures, while the infrared heating rate becomes lower under a higher temperature. So it means when we use infrared heating under a higher temperature, more time is needed than expected. And additionally, infrared heating rate was lower than microwave heating rate under 5 kilowatts power, as we can see, but it becomes the opposite side when the power was 10 kilowatts. It also shows that increasing the power can increase the infrared heating rate more effectively than microwave. In terms of the energy consumption, the microwave heating time was found proportional to the power. So the energy consumption under different powers for microwave is the same. But for the infrared heating, the total energy consumption would decrease gradually when the power increases. And under the same heating power, the energy and time needed for infrared heating is much more than microwave heating. So overall, microwave can heat the pavement to a greater depth, while infrared heater can only heat the shallow area of the pavement. To heat the internal area of the pavement, maybe cooling cycle is necessary for infrared heating, while the total time needed is much more than microwave heating. And from energy consumption point of view, increasing the microwave power would not increase the energy consumption, but can reduce the heating time. While for infrared heating, it needs much more energy than microwave heating under the same power. So the microwave shows a great potential to be applied in hot in-place recycling. And this study is still ongoing. The authors will conduct field tests and observation in the future by using microwave and infrared heating. That's pretty much of my presentation, and thank you for your watching and listening.
Our next poster is titled An Innovative Green Pervious Concrete Made with Modified Geopolymer Materials, that is presented by Rutgers University, Huang.
Hello everyone, it's happy to be here to share my study with you. Today my presentation title is An Innovative Green Pervious Concrete Made with Modified Geopolymer Materials. As we know, the pervious concrete is a typical type of concrete with interconnected pores. Usually it is made with cementitious materials such as cement and coarse aggregate. Owing to its unique porous structure, it is beneficial in several pavement applications, such as the stormwater mitigation, the urban island heat reduction, the vehicle noise reduction, and the pollutant water purification. However, the relatively lower mechanical strength of pervious concrete largely limits its applications, and the use of cement is also proved to be the major source of carbon dioxide emission. Thus, it is designed to fabricate pervious concrete for superior performance while reducing the carbon footprint. Recently, alkaline-activated geopolymer has been developed due to its better durability and environmental benefits. It does not release carbon dioxide during production, and many waste materials or byproducts can be used as raw materials. It is designed to apply the geopolymer in pervious concrete without interfering its original porous structure and enhance its mechanical performance. The geopolymer-based pervious concrete has high potential to be applied as green pavement materials. The study aims to develop and characterize two types of geopolymer-based pervious concrete, which are the Mitigation and flash, and improve their performance through chemical modification with granulated blast furnace steel slag, denoted as GBFS. The microscale characterization and the mechanical strengths of the modified pervious concrete are mainly investigated. As for the preparation, the Mitigation or the flash powder are firstly mixed with GBFS at different content. After this mixing, the powder then mixed with the alkaline solution, which is the sodium silicate and the sodium hydroxide. The cubical specimens with dimension of 2 inches are prepared, and the microanalysis, including the XRD and the SVM and the mechanical test, which is the compressive test, are applied on the geopolymer paste specimen to optimize the formula. After optimizing the formula, then we use this formula to mix with aggregate to prepare the geopolymer pervious concrete. Here, the aggregate is a limestone, and it has 4 different gradations with different sizes, denoted as F1 to F4 as shown in Table 1. After the preparation, we applied the mechanical test, which are the compressive test and the splitting tensor test on the geopolymer pervious concrete. These samples are the cylinders with 4 by 8 inches dimension. As for the result, the compressive result of the geopolymer paste are shown in Figure 5. All geopolymer paste specimens could achieve considerable high compressive strength by ambient curing condition. And also we can find that 10% and the 30% of the GBFS content are the optimized dosage to achieve the highest compressive strength for the geopolymer paste specimens. As for the microanalysis, we can see here. First is the XRD result. As for the metakaolin-based geopolymer paste, after introducing the GBFS, we can find that there are several new crystal faces generated. And as for the flash-based geopolymer paste, we can find, well, it has much more complicated chemical components compared with the metakaolin-based. And also we can find after introducing the GBFS, there is no apparent difference between them in the new phases. We also did the SEM test on the geopolymer paste specimens, and we can see here, there are several defects such as the voids, the cracks, the unreacted particles. And so we transform the SEM images into the binary image, and we use the white area to denote the defects. And we use the image analysis tool to calculate the total defects area. The results are listed here. We can find the metakaolin-based geopolymer paste with 10% of GBFS has the lowest defects area, which is 3.6%. And also we can find the flash-based geopolymer paste with 13% of the GBFS has the smallest defects area. This result is accordance with the compressive result. Combining this result, we can finally determine the formula, and we use this formula to prepare the geopolymer-based pervious concrete. And we did the porosity test and the permeability test on the porous concrete. The results are shown in Table 2. We can find the specimens with gradation A1 will have the highest porosity and also the highest permeability. And also the correlation between the porosity and the permeability is linear. We also did the compressive and the splitting tensor test for the geopolymer pervious concrete. Results are shown in Figure 8. We can find here, the porosity is a major influence factor. With the reduce of the porosity, the compressive strings and the splitting tensor strings will increase. However, when the porosity are the same or are similar, if we compare the metakaolin-based pervious concrete with A1 to A3, as shown here, they have similar porosity, but their compressive strings reduce, their splitting tensor strings increase. So this phenomenon indicated that there is another factor that affecting the variation of the strings, which is the size of the aggregate. We back to Table 1, we can find the A1 has a smaller size, the F3 has a larger size. So we believe the aggregate size affects both compressive and splitting tensor strings of geopolymer-based pervious concrete. If we further compare the specimens with F3 and F4, we can find that their compressive strings increase from F3 to F4 for both metakaolin and flash-based pervious concrete. However, their splitting tensor strings reduced from F3 to F4. So we believe the sand has positive effect on compressive strength, but a negative effect on splitting tensor strings. The reason is because if we have more smaller particles, the interaction between the aggregates will be more complicated, and the friction during the compressive test will be higher. So the compressive strength is higher. However, for the splitting tensile strength, which is mainly coming from the bonding effect between the paste and the aggregate. So if you have more smaller particles, which means the thickness of the paste coated on the surface of the aggregate will be thinner, and the bonding effect will be weaker. This is, as a consequence, the splitting tensile strength will be reduced. In general, we found the ambient temperature curing was sufficient to develop high strengths of geopolymer paste and Pervious concrete. And also we found the new crystal phases were observed in the excited result after introducing the GBFS into geopolymer. And also we found the optimized GBFS content could provide better integrity and less cracking, voids, and unreacted particles in the paste materials, as we can see from the SEM result. We also found the lower porosity induced higher compressive and splitting tensile strengths. However, smaller aggregate size induced higher compressive but lower splitting tensile strengths at the same porosity. That's all. Thanks for listening.
Our third poster is titled Modeling and Mitigation of Thermal-Induced Reflective Cracking in Asphalt Concrete Overlay, and it is presented by Rutgers University's Pengyu Issa.
Hello everyone, thank you for joining me here at this poster session. I'm Pengyu Issa from Rutgers University. I'm here today to talk about the modeling and mitigation strategy for thermal-induced reflective cracking in asphalt overlay. As we know, asphalt concrete overlay is an efficient and effective method to rehabilitate deteriorated pavement and restore structure capacity. However, cracks always reflect to the overlay from the discontinuity in the existing layer under traffic loading and temperature cycles. In this study, we focus on thermal-induced reflective cracking in asphalt over rigid pavement structure. The diurnal and seasonal temperature cycles generate contraction and curling effect in the underlying concrete slabs, tearing apart the asphalt overlay gradually at low temperature. Theoretically, reflective cracking belongs to the category of fatigue cracking, which cannot be formed with one-time loading. A number of studies has been conducted to estimate crack initiation and propagation rate. We can categorize them into two groups. The first one uses fatigue models to relate critical stress and strain to the loading cycles in the fatigue test. The second one considers fracture mechanics that use stress intensity factor or J integral to capture the stress status at crack tips. The fatigue life can be estimated by the Paris law. People have tried many methods to mitigate reflective cracking, like increasing overlay thickness, adding interlayer or reinforcement, modifying the asphalt mixture. So in this study, we developed our own model to simulate thermal-induced reflective cracking and analyze how the overlay thickness and stress-absorbing interlayer affect the cracking. We start from developing finite element models. The FE model was used to calculate pavement responses and stress status at crack tips. Two loading conditions were considered. The displacement-controlled loading model fixed one slab and gave another slab a horizontal displacement to simulate joint opening. This model is used to calibrate and validate our model with test results. The second model is real thermal loading model, which consider a temperature drop in the pavement structure and analyze the temperature effect and mitigation strategies for thermal-induced reflective cracking. The refined mesh were given in the asphalt overlay right above the joint to keep the convergence of the results. The stationary crack were considered in our model. The crack initiation cycle was estimated by the stress-based fatigue model. The model was derived from low temperature and low frequency beam fatigue test, which is similar to the actual thermal loading. The crack propagation is calculated by the modified Paris law based on the J integral derived from the FE model. The fracture parameters A and N can be calculated from material properties and loading frequencies. The simulation results was calibrated and validated with the field test at national airport pavement test facilities. They design and built temperature effect simulation system to evaluate reflective cracking by horizontal displacement instead of the real cooling process. We use the measured tensile strain along the depths in asphalt overlay to calibrate our FE model, and then use the calibrated FE model, fatigue model, and the Paris law to calculate crack initiation and propagation cycles in different overlay thickness. It can be seen that the proposed model can roughly capture the trend of thermal-induced reflective cracking. Considering the uncertainty of fatigue process, this validation is acceptable for current studies. It can properly simulate the reflective cracking in asphalt overlay. The next step is to use the real thermal loading model to analyze mitigation strategies for thermal-induced reflective cracking. In order to generate thermal load, we used climate data from LTPP database to calculate pavement temperature and select a typical cooling process in winter. The air temperature we selected drops from -4 degrees Celsius to -12 degrees Celsius. Two mitigation strategies were considered. The first one is increasing overlay thickness. We considered 3-inch, 5-inch, and 7-inch overlay thickness in this study. The second one is stress-absorbing interlayer. The bottom 1-inch overlay was replaced by the softer interlayer material. It should be noted that the interlayer is softer and has much higher fracture energy at low temperature, so the reflective cracking will not generate in the interlayer material and still initiate from the bottom of surface mixture. The bottom figure shows the crack cycles number with different overlay thickness. For thin overlay, such as 3-inch overlay, increasing 2-inch thickness makes the new cycles almost 3 times longer, while for 5-inch overlay, increasing the same 2-inch thickness will get the total cycle twice longer than before. So the increasing overlay thickness may not be very effective for thick overlay structure. The right top figure plots the stress and strain distribution along the overlay depths. Below the red line is the interlayer material. Although the tensile strain in the interlayer is larger than the counterpart in the control section, the critical stress at overlay bottom has been reduced by 1/3, which means the crack potential is reduced. The total cycle numbers for the interlayer section are several times larger than those in control sections. And if we compare these two methods, increasing 2-inch overlay and applying 1-inch interlayer, the interlayer method shows better mitigating effect but uses less budget. So for the thermal-induced reflective cracking, adding interlayer is more cost-effective than increasing overlay thickness. However, the current study and conclusion only focus on temperature effect. A more comprehensive analysis that considering both thermal and traffic loading should be conducted in the future. Thank you very much. That's all for my presentation.
Our next poster is titled Understanding the Interconnectivity Between Intersection Traffic Congestion and Outdoor Air Quality for Smart Cities, that is presented by Rowan University's Kourtney Arena.
Traffic emissions continue to be a prevalent source of air pollution across the globe. Those living in high-traffic urban areas are at higher risk for developing or exacerbating respiratory health problems. Stop traffic at intersections allows for concentrated areas of emissions, and of those pollutants, polycyclic aromatic hydrocarbons, or PAHs, are particularly concerning due to their connection to a variety of health problems. There are a number of pollutants regulated by the EPA as well as other agencies, some of which I have listed here. So PM 2.5 is regulated by the EPA for 12 micrograms per meter cubed for 24-hour mean exposure. And PM 10 is regulated for 150 micrograms per meter cubed per 24 hours mean exposure for the health concern of aggravation of cardiopulmonary diseases. Nitrogen dioxide is regulated by the EPA for 100 milligrams per meter cubed per hour of exposure. Also for aggravating respiratory diseases, as well as being linked to the development of asthma. PAHs, on the other hand, aren't regulated as a whole. There are a few regulations out there for various PAHs. However, BAP is of particular concern. That's benzoapyrene. While some PAHs are known to be cancerous, BAP is specifically known to be cancerous to humans, and the NIOSH regulates it for 0.1 milligrams per meter cubed for 10 hours of exposure. And they are linked to the aggravation of cardiopulmonary diseases as well as various cancers. VSIM was used to create a model of the intersection of Haddon Avenue and Dr. Martin Luther King Jr. Boulevard in Camden, New Jersey. To create this model, traffic count data, lane geometry, and traffic signal timing were used. The latter two were from Camden County. The traffic count data was taken from the NJDOT 48-hour traffic count for Dr. Martin Luther King Jr. Boulevard, Haddon Avenue, and North 7th Street, which transitions into Haddon Avenue. This volume was used to create the baseline conditions for case 1, which explored the following scenarios: 1 to 2 p.m., 2 to 3 p.m., and the average peak hour, which was between 3 to 4 p.m. and 4 to 5 p.m. as it varied on different days. Then for case 2, the traffic control devices were removed to evaluate free flow conditions. And then for case 3, the baseline traffic volume was doubled. From running these sims, we got link length, volume, average speed, and source type fraction, which were then input into MOVES S3, which was used to model the particulate matter and nitrous oxides emissions. Here you can see our results for the cases. PM 2.5 and PM 10 were slightly higher in April than in March, and increased emissions did correlate with an increase in linked traffic volume, which is to be expected. Going from case 1 to case 2, which is the baseline, to the free flow conditions, there was an 18 to 24% decrease in particulate matter and a 5% to 0.1% decrease in nitrous oxides for 1 to 2 p.m., 2 to 3 p.m., and for peak hour, respectively. The exact reason as to why these are much lower, we're not entirely sure of. It may possibly have something to do with an increase in speed. However, that increase would look something like 10 miles per hour to 20 miles per hour. So we're not entirely sure that is the contributing factor to that. Going from case 1 to case 3, which the baseline to the doubled traffic volume, we found a 31 to 59% increase in particulate matter and a 33 to 59% increase in nitrous oxides. And these numbers are actually lower than what they should actually be, as when running the VSIMS model, we found a capacity issue in which, specifically looking at the southbound portion of Haddon Avenue, in each one of our runs, about 100 vehicles or so from that link were not able to make it through the intersection within the given time period. So we expect those actual numbers to be higher. From our current position with our research, we would like to perform a second-by-second simulation in MOVES S3 using VSIM data to have greater detail of what's actually going on at the intersection in our model. Then we would like to simulate emissions using AirMod as opposed to MOVES S3. That way we can sort of compare our emissions output. Then Earlier this year in March and April, we had collected PM and PAH air samples, and we are looking to further collect samples in the later part of this year. Once we get those analyzed, we will attempt to find a correlation between the particulate matter and PAH emissions for the intersection in question. And once doing so, we will then compare our model at another intersection to test its validity. And if all goes well, we will then be able to propose a model to help city planners reduce emissions at intersections.
Our fifth poster is titled Estimating Roadway Horizontal Alignment Using Machine Learning and is presented by New York University's Bekir Bartin.
The title of the poster is Estimating Roadway Horizontal Alignment Information Using Machine Learning. This work is a byproduct of a recent New Jersey Department of Transportation research project titled Calibration and Development of Safety Performance Functions for New Jersey. So the motivation for this work is that roadway horizontal alignment data being very crucial and necessary information for various safety analysis, yet the information is not readily available in many states' roadway inventory databases. And the necessity for this data has become very clear since the publication of HSM in 2010. As a result, many researchers wanted to get very fast and accurate curvature information using satellite images. However, extracting this information, especially for an entire network, it takes a significant amount of time and resources. And more often than not, the quality of the extracted data is often questionable. However, there are available GIS databases which can be leveraged and used for this specific purpose. To that end, the objective of this work is to introduce an artificial neural network-based road horizontal alignment estimation method, which uses GIS roadway centerline data and to evaluate its accuracy. The proposed method is first trained using GIS roadway alignment data, and then applied to a new network, new roadway of which the actual alignment information is known beforehand. So the problem definition is as follows. We can consider a roadway as a smooth function which consists of various tangent and curve sections. And the GIS nodes or vertices are discrete points that represent this smooth function. It discretizes this smooth function. And now we can look at this, for instance, this roadway, and can tell visually where the tangent sections and the curve sections are. But how do we do this automatically? So if we knew how many distinct tangent and curve sections there were, and we knew the start and end of these sections, we can use, for instance, curve fitting techniques to estimate the radius and the length of a curve section and the length of a tangent section. However, with the lack of such information, it makes it a very difficult problem. So the proposed approach is a two-step process. One is segmentation, meaning where are these sections and which ones are the tangents and which ones are the curve sections, and determine where they start and where they end. And the second part is using the information obtained from the first step, use curve fitting. Especially in this work, we use Tobin fit method. And we use artificial neural network method in step one. Basically, we use several explanatory variables for each vertex. And the idea behind this is that whether a point or a vertex is a part of a curved or a tangent section, it can be identified by several variables. These are heading angle, curvature, change in heading angle, distance between consecutive vertices, the milepost information, radius of a circumscribed circle, cumulative change in heading angles at 3 consecutive points, and the difference in cumulative heading angles around each vertex. So these are various explanatory variables used in the literature, so we combine all of it, and there is, for each vertex, we have a vector alpha, including these vertices. So using these, and also the information that whether a vertex is a part of a tangent or a curve section, we can train the neural network and find out, using these explanatory variables, find out whether a new vertex given to us is a part of a curved or a tangent section. And the data set we use, we train, the first one is for training, validation, and test of the ANN model. We use two different data sets. One is from abroad, and the other one is from New Jersey. So we use this data to train the ANN network. And the second one is the evaluation data set. It's a freeway segment on I-80 in Nevada between mileposts 15 and 25.72. So it is over 10 miles long, and it includes 10 curves. And the alignment information is obtained from the literature, where the curved locations of the curve sections and the respective radius values are tabulated meticulously. And we obtained the GIS roadway centerline shape file from the Nevada DOT website. And using the ANM method for the segmentation, and also using the Tobin fit method for the curve fitting, we show the evaluation results. And when looking at the evaluation results, the proposed method finds all the curves and tangent sections, all of it. And the overlap ratio of the estimated curve lengths with the actual ones is 97%, and the total undetected curve length is nearly 0.11 miles on average. And the similar overlap ratio for the tangent section is 92%, and the total undetected tangent length is 0.5 miles, which is 261.5 feet on average. So we expect such discrepancy because the vertex resolution for this specific GIS network is about 183 feet between two vertices. So looking at the results, we also detected one more curve additional to the ones that were reported, which has a radius value of more than 10,000 feet, and it was not reported in the original data, but the authors stated that they dismissed that curve because the radius value was more than 10,000 feet. So this shows the accuracy of the proposed method. So as for the conclusions, the study shows a very novel approach for estimating roadway horizontal alignment data that utilizes machine learning, specifically artificial neural networks, trained using available roadway horizontal alignment data. Because extracting such data is time-consuming and costly, an efficient and fast method is required because this information is crucial in various safety-related analysis, especially in highway safety manual for different roadway types. Curvature information is essential in calculating the crash modification factors. So the proposed approach takes advantage of the available GIS centerline shapefiles, and they're available for nearly all roadways in the United States. If you have any questions or comments, please, you can email me at my email address, which is Bekir. It is BBARTIN@gmail.com. Thank you very much for listening.
Our next poster is titled Influence of Cracking and Brine Concentration on Corrosion and Chloride Content, that is presented by New Jersey Institute of Technology's Aaron Strand.
Hello, my name is Aaron Strand from NJDOT, and today I will be discussing my project titled Influence of Cracking and Brine Concentration on Corrosion and Chloride Content. Corrosion of steel reinforcing bars is the most commonly observed deterioration mechanism in concrete structures. Reinforced concrete bridge decks and pavements particularly those in areas where de-icing chemicals are applied to roadways, are highly susceptible to deterioration from corrosion of the reinforcing steel caused by chloride ingress. Bridge decks will freeze before surrounding roadway and thus are of particular attention for de-icing when freezing conditions are expected. In order to ensure a safe roadway for travel, de-icing is done typically with high chloride concentration brines. This is compounded by cracking of the concrete deck due to conditions such as live loading, thermal loading, and concrete shrinkage. These cracks can develop at early ages of a bridge's lifespan, even soon after initial construction. The depth of the crack will provide an effective reduction in the cover depth above the reinforcement, and at worst may provide a direct path to the reinforcement for the chlorides. For this project, the impact that brine concentration and the presence of a crack has on laboratory-based corrosion testing was looked at. The early results from this study were used as a companion and guidance on a larger scale model bridge deck specimen, which was subjected to freezing and thawing cycles, a moving load, and applied de-icing salts. For laboratory testing, ASTM G109 was used to monitor the macrocell corrosion that develops between the upper and lower reinforcement. Corrosion is stated to have initiated once the specified threshold has been met. In this test method, the chloride concentration is held constant at 3% by weight, though for this testing, 5 different chloride brines from 1.5 to 9% were used. This was done to simulate the impact that different concentrations of brine from factors like the application amount, the deck surface topography, and weather conditions have on bridge decks. To measure the impact of cracks, each brine concentration had one specimen in the uncracked condition and another in the cracked condition. After the macrocell corrosion testing was completed, powder profiles were taken of each specimen in which the acid-soluble chloride content was found. From the bridge deck specimen, cores were taken at different times and profiled for acid-soluble chloride content. The acid-soluble chloride content results were used to calculate the apparent diffusion coefficient and the chloride content of the deck surface. From the macrocell corrosion results, the 10 microamp current threshold was reached for all cracked specimens, though the threshold was not consistently exceeded for the specimens ponded with 1.5 and 4.5% brine by the end of testing. For the cracked specimens ponded with 3% brine or higher, the threshold was reached within the first 2 ponding cycles. Though at 4.5% brine, the macrocell current dropped below the threshold after 7 cycles. Of the 3 specimens that had a macrocell current exceeding 10 microamps at the end of testing, the cracked 9% brine specimen had the highest average macrocell current with an average of 85 microamps during the wetting part of the cycle and 75 microamps during the drying part of the cycle. In the uncracked specimens, the 10 microamp threshold was not exceeded during the testing period. The largest current result collected from the uncracked specimens reached a value of 1 microamp, which is 10% the 10 microamp threshold value. The small values and fluctuations are likely due to the sensitivity and error within the voltage meter and testing setup. From these results, the corrosion potential of cracked systems is observed in general to be much greater than that in an uncracked system. The presence of a crack results in a macrocell corrosion value that exceeds the threshold to initiate corrosion of the reinforcement at early ages if sufficient chloride is present. This correlates to literature in measurement of chloride in bridge decks where the early age presence of cracks within a concrete deck resulted in higher rates of corrosion. The total integrated current, or total corrosion, was also calculated. The specified corrosion threshold in ASTM G109 of 150 coulombs was only reached for the specimens that were cracked and ponded with a brine concentration of 3, 6, or 9%. For the uncracked specimens during the testing period, the total corrosion did not exceed the value of 1 coulomb for any of the tested specimens. This shows a major difference between the rate of corrosion in cracked and uncracked systems. The result of the specimen ponded at 6% reached the integrated current threshold faster than that of the higher concentration of 9%. This may be due to the fact that this specimen had the largest crack width of all tested specimens at 0.3 millimeters. The next largest crack width of a specimen was at 0.2 millimeters. From the chloride profile data, the concentration of brine does seem to impact the amount of chlorides that were found within the samples at a given layer. The higher the brine concentration, the higher the chloride content that was found. Near the surface, the chloride content was similar between the cracked and uncracked conditions of each of the brine levels. The biggest difference was observed between the 6% brine cracked and uncracked specimens. Again, This is likely attributed to the higher crack width of the cracked specimen compared to the rest of the cracked specimens. At the reinforcement, the cracked specimens have noticeably higher chloride contents, with the chloride content of the cracked 1.5% brine found to be higher than that of the uncracked specimen ponded with the highest 9% brine. This highlights the importance of understanding the cracked system's rate of chloride ingress. To calculate the diffusion coefficients, a least squares regression analysis was used to fit the curve to the data, varying the surface chloride content and the diffusion coefficient. The apparent diffusion coefficients found were higher in the cracked systems than those found in the uncracked systems. Except for the specimen ponded with 6% brine, the apparent diffusion coefficients for each of the uncracked specimens was found to be similar, with an average coefficient of 2.64 e to the negative 12 meters squared per second. The apparent coefficient of diffusion for the uncracked 6% brine was 64% larger than the average of the other uncracked specimens. For the cracked specimens ponded with 1.5, 3%, or 4.5% brine, the apparent coefficients of diffusion were found to be about 2.25 times greater than their corresponding uncracked coefficients. The change was less between the 6% brine cracked and uncracked specimens, with an increase of 47%, and was larger for the 9% brine specimen, with an increase of around 5 times. The method of calculating the diffusion coefficient is based off of Fick's second law of diffusion, and due to this, when used for a cracked system, the resulting chloride content curve does not correspond to the found data. This also means that the resulting diffusion coefficients do not accurately capture the crack condition. The diffusion coefficients calculated from the cores taken after 3 months of exposure at the bridge deck were larger than those found in the laboratory tested specimens, though the values dropped as testing progressed due to the lack of greater chloride ingress and the longer time of testing duration. Also a factor is that the cores were taken from similar locations but not identical, and these locations were not at the worst deteriorated areas of the deck due to complications of extracting cores from these locations. These results of testing corrosion of embedded reinforcement at various brine concentrations and cracking conditions show that the presence of a crack and the ponding brine concentrations have an effect on the rate until corrosion can initiate, the measured chloride concentration of the concrete, and the apparent coefficient of diffusion of the system. Overall, the data shows how the presence of a crack within the system will greatly reduce the time until corrosion can initiate when a sufficient brine concentration is present. The study also validates the importance of using multiple factors in testing for corrosion due to the nature of compounding impacts of environmental conditions and not just basic testing and modeling of diffusion alone.
Our next poster is titled Supporting Bridge Deck Condition Assessment Through the Use of TLS and is presented by Rowan University's Issa Al-Shaini.
Good afternoon, ladies and gentlemen of the New Jersey Department of Transportation, NJDOT. My name is Issa Al-Shaini. I'm on a graduate fellowship pursuing my master's degree at Rowan University. This presentation is made for the 23rd Annual Research Showcase, supporting bridge deck condition assessment through the use of terrestrial laser scanning, also known as terrestrial light detection and ranging scanning, LiDAR scanning. This presentation was prepared by my graduate advisor, Dr. Adriana Treas Blanco, and me, Issa Al-Shaini. Starting to talk about our project goals. As we have been studying the various methods used to contribute in bridge condition assessment, specifically bridge deck condition assessment, the non-destructive methods used currently, such as ground penetration radar, GPR, bridge deck slope analysis, electrical resistivity data analysis, and much more commonly used non-destructive assessment methods, all failed to provide sufficient data of the geometry of the surface of the deck. Our goal starts here, and it is to explore and exploit light detection and ranging geometry scans, LiDAR geometry scans, for structural health assessment. We will need to quantify terrestrial laser scanning contributions on supporting bridge deck condition assessment. For our research, we are using the Faro-Focus S scanner, and our research will be conducted on bridges in New Jersey state. A total of 8 bridge decks will be scanned in the state of New Jersey. During this research, our team will focus on 2 main objectives. First, to analyze the correlation between the deck's surface geometry and the reported condition rating obtained from the InfoBridge website by the National Bridge Inventory (NBI). And secondly, to evaluate the impact of deploying terrestrial light detection and ranging LiDAR scanning as a screening tool to prioritize detailed deck inspection. In order to have a better idea on our project, we need to have a look at previous results obtained from the NBI, the National Bridge Inventory, through previous assessment methods used. Taking bridge structural number 0832162 for example. The results for 2 different assessment methods were obtained from the NBI, National Bridge Inventory. A bridge deck slope analysis and an electrical resistivity data analysis were conducted on bridge number 0832162. By having a look at the results obtained from the 2 different assessment methods, we can tell from the bridge deck slope analysis, by looking at the gradient of the color for the left side of the bridge, we can tell it has a flatter slope than the right side of the bridge. The results showed that the left side had a 0.43% slope, while the right half of the deck presented a slope of -1.82%. Taking a look at the electrical resistivity data analysis, it shows that the left side of the bridge presented higher levels of potential corrosion than the right side of the bridge. By combining the 2 results from the 2 different assessment methods, we can indicate that the steeper slope on the right half of the deck is allowing water to run off the deck easier, minimizing deterioration effects. On the other hand, for the left side, the flatter slope is causing sometimes water retention on the surface of the deck of the bridge and causing the bridge to deteriorate and the steel to corrode. It took us 2 different assessment methods to get the result that water retention is causing this bridge to causing the left side of the bridge to be on higher levels of potential corrosion. By having a look on the scans obtained by our team, our research team on the field, we can see that we were able to provide data directly about the geometry of the surface of the deck, which was not present in any of the previous assessment methods used. As we can look at the scan on the top right corner, this is a registered scan through Scene software. The scan was taken by the Faro-Focus S on one of the bridges in New Jersey. The gradient in the middle of the bridge, the green region, it shows a flat slope where the gradient is not changing. In the middle, it turns into yellow and darker, which can indicate a depression on the surface of the deck, which may lead to water retention and eventually lead to potential failure and corrosion. We were able to get the result by registering our scans and colorizing the scans to to vary between different elevations. The right side here shows the sidewalk, and it shows that it elevates higher than the deck surface. Finally, for our data analysis and expected results, we will compare the data obtained from the field for the 8 bridges with the data from the National Bridge Inventory, the NBI, so that hopefully terrestrial light detection and ranging scanning assessment will help in detecting vulnerable areas and predict deteriorating patterns. And for the next time, we'll try to include the ADT, the average daily traffic, and the TADT, truck average daily traffic, as a percent of the average daily traffic to be considered during the analysis in our research. Thank you for your time.
Our final poster presentation is titled New Brunswick Innovation Hub Smart Mobility Testing Ground Data City, a smart and autonomous initiative that is presented by Rutgers University, Xiao, Huang.
Hello, everyone. Thank you for joining our poster session. This poster is about New Brunswick Innovation Hub Smart Mobility Testing Ground. This is part of the NJDOT research project 21-60168. The purpose is to deploy a 2.1-mile smart mobility testing ground corridor in the city of New Brunswick along Route 27 and Route 18. The project dates back to our participation in the inaugural Innovation Challenge hosted by New Jersey Economic Development Authority. We are one of the 9 communities, together with the City of New Brunswick and DEVCO, to develop a conceptual plan of creating a data bed and testing ground for the New Brunswick Innovation Hub. Since then, the project was officially funded in 2021 for the deployment on Route 27 and Route 18, and is currently also under contract with the Middlesex County to potentially expanding that to a county corridor and building the state-of-the-art operation and mobility management center for the testing ground. The key concepts of the Data City Smart Mobility Testing Ground includes first creating a New Jersey mobility technology breeding ground to test out and conduct R&D of different smart mobility technologies. It includes creating the Smart Mobility Management Center that is part of that will operate and operates the entire testing ground, all the instrumentation, and together with building the Traffic Operations Center for Middlesex County. The testing corridor will be equipped with industrial-grade smart mobility sensing computing technologies that's currently used by self-driving cars. That includes LiDAR and computer vision sensors and edge compute sensors. With the data collected by those sensors, the testing ground will create a data sharing hub to support academic, industrial, and public sector R&D. And we will be creating a digital twin platform to support early stage R&D for those technology to be tested with real-world data. A V2X-based smartphone-based community mobility applications will be developed to potentially creating the testing interface for local community, and also for the future deployment of mature technologies to be used in the testing ground. The smart mobility data services include high-resolution video and LiDAR data collected from our roadside sensors, and also the converted vehicle and pedestrian and other object trajectory data, and as well as infrastructure condition data, which will be packaged into a data service that can be provided to the public, private, and academic communities. The proposed testing ground will be managed by a smart mobility management center, which features development space, server rooms, and also most importantly, the state-of-the-art video wall, including a 180-degree curved wall for visualizing high-resolution data that will be collected from the testing ground, and also the flat screen to support normal traffic operations and monitor multiple cameras and sensor conditions along the corridor, and also to support Middlesex County traffic operation. There are many applications that will be demonstrated and tested in this project, including intersection near-miss detection and alerts, pedestrian safety applications, community mobility applications, and also autonomous shuttle program in collaboration with Verizon's VZ mode technologies. The purpose is to establish potential first and last mile routes to support hospital operations and patient and patient family movements, and also potentially in future traffic going in and out of the New Brunswick Innovation Hub that has recently breaking ground last week. The testing ground is also in close communication with industry to potentially supporting self-driving car and truck and delivery technology testing. We are part of one of our PI is part of some of our PI is part of the technology task force that will provide recommendations for the authorization and testing of self-driving technologies in New Jersey. Here's a detailed picture of the instrumentation, which includes the Velodyne Prime VLS 128 beam LiDAR, the Blue City Edge compute boxes, Iteris Bosch camera and roadside units, and also we'll be working with Verizon's VZ mode technology that deploys connected vehicle technologies through their 5G towers along the corridor. A digital twin model will be created to allow testing of different self-driving technologies in the virtual world, creating real-world scenarios to accelerate self-driving technologies development and training, driving model training, especially for the northern region with different weather and traffic conditions compared to the current testing in the southern states. Finally, this is our contact information. Feel free to contact us if you have any questions regarding our testing ground effort. We will keep everyone posted on our latest progress. Thank you.